two more things to quickly wrap up as well. And first of one of them is being Kepler's law. And Kepler's law is where you can really see the power of now using all the concepts in physics you've learned to make great predictions that go way beyond the Earth. And now you can actually, as just a mere mortal standing on the Earth, you can actually understand how does the solar system work from just a couple of equations we've learned. All right. So what do I mean? Let's derive a relationship between anything going around a circle due to gravity. Okay. So I don't care what that is. It could be the Earth and the Moon. It could be, let's make that a little bit more symmetrical, right? It could be the Earth and the Moon. It could be the Sun and the Earth. It could be the Sun and Jupiter, Sun and any other planet or whatever. So anything going around a circle due to gravity. So we have a universal force of gravity, so of attracting it. And now you understand this is also a circular motion. So this is acting as the centripetal force. So if you remember what you learned in centripetal forces, so how do you analyze this situation is you ask what are the centripetal forces, and then you equate this to mv squared over r, right? So in this case, the centripetal force is just the force of universal gravity that way. Okay, and there's nothing else. There's nothing else acting on the test object. So this is the source. This is the test object. Okay, so the test mass and the source. Okay, so the source is going to be denoted by capital M. The distance is going to be denoted by r. And now you see why we use r is because a lot of times when we analyze these things, it's going to go in a circle. So the distance between them, we use r for radius. And this is going to have little m. Okay, so we're going to plug in, right, gmm over r squared. That's the magnitude of that force. We're going to equate that to mv squared over r. Now we need to be sure, do we understand which m, which v, which r? Because we have two m's over here. So should I put the big M or little m over here? Should be little m because this is talking about the centripetal force that the test object is experiencing, right? With the force of gravity is the test object and the source object, okay? Source mass and the test mass. So you put the test mass, it's always the test mass over here. And if that's about the test object, the velocity has to be about the test object as well. So that's the velocity or the speed, right? It's going to be a constant speed around here. And how do I know it's a constant speed? Because let's say it has some speed, then the force of gravity is never going to accelerate that speed because you do not have any components. If you resolve this, there's no component going in this direction, the tangent direction. So there's no tangential component, only a radial component. So you know it's going to be a uniform circular motion. Okay. So we understand that r is r the same r as that. Whenever you have duplicate variables, ask yourself, is it the same variable? And it should be, right? Because this r here should be the radius of that. So you are measuring it from the center of mass to the center of mass as the radius of the circle. And this is talking about so they actually mean different thing. It just happens to be the same variable. It's happen to be the same quantity, right? This tells you the radius. What you're supposed to put here is the radius of the circular motion, right? And what you're supposed to put here is the distance between the two masses. The two masses center of mass. Right? And it just happens in this case, they're the same. So a lot of mistakes from physics students comes from you remember one formula, there's an R, you remember another formula, there's an R, and you just put it together without realizing they could be different. And sometimes they are, 50% of the time they are, 50% of the time they aren't. So 50% of the time you make a mistake if you don't understand what they are. So this is why understanding is very important. So what can you learn from this? Is your life any better from making this equality? Well, let's see what we can learn. Well, first of all, the two m's over here, the two r's, it's almost begging you to simplify this equation a little bit. So please do it, right? And what do we find? Well, we find v squared is equals to gm over r. This is a very important relationship that we realize if you know the speed of for example, the moon, right? And if you know the speed of the moon, and if you know the mass of the Earth, you can find out what the distance is over here. Okay, you might ask, how do I know the mass of the Earth? Well, you can pick up a rock from Earth, and so this is one way to do it, right? You can pick up a rock on Earth, and assume the whole Earth is roughly made out of this rock. Again, we're doing with order of magnitude estimates. We can do that more and more accurately as technology improves, but let's go back to the Greeks and find the easiest way that you can do it almost without a calculator and without any fancy equipment. You pick up a rock, you can find the density of the rock, all right? The density in physics is usually given by rho, again, not P, it's the Greek letter rho. Yeah, it's the Greek letter for R. Don't ask me why it looks like that. You can ask the Greeks, but so you can, what is density? It's mass per unit volume, right? So, all right, so you pick up a rock, you weigh it, you figure out, okay, what's the mass? You measure the volume, all right? So maybe pick up a square, it's easier to get a volume or whatever, put it in water, find out what volume of water it displaces. This is Archimedes method. You put it in here, figure out what volume of water get displaced once you put the rock in here, and you can measure the volume of the water in the beaker, right? And now you figure out, okay, I know the density of the rock. Well, let's assume the whole Earth is made out of the same rock. It's it's rough estimate. It'll give you the right order of magnitude, right? It might not give you the correct coefficient, but whether it's 10 to the power of 23 or 10 to the power of 24, it'll give you roughly correct this power. You're not gonna drastically, you know the difference between 10 to the power of 24 versus 10 to the power of 13, right? If you do this, you're not gonna have, 11 digits of power of tens. You're not gonna be a million times off. And a million is only 10 to the power of 6, right? So you're probably going to be like 10 times off, 100 times off, worse, 1,000 times off, but it's going to be roughly the right thing. So assuming the whole Earth is made of the same density, okay, so what's the mass of the Earth? Well, the mass of the Earth is going to be the density times the volume, right? The density of Earth. So you assume the density of Earth is the same as, or roughly the same as the density of the rock. So once you've calculated this, you know this. And how do you know the volume? Well, assume the Earth is a sphere, which first order it is. And now you can know volume of a sphere is 4/3 pi r cube. And r over here is the radius over there, right? So the radius of the Earth is something you can measure by curvature, from trigonometry, like look at the shadow of a sun on a pole, you can measure the radius of that. So you can easily find the volume of the Earth, and you can find the mass of the Earth. So that's one way. So let's say you find the mass of the Earth, and as I said, you find the radius of the Earth, and now you can also try to measure the velocity of the moon. But it's easier to measure the period of the moon, right? Because we know how long does the moon go around the Earth? Well, the period of the moon is around 27.3 days, right? Around a month, right? Around just under 28 days, right? So that's something you can measure, and it's easier to plug in the equation. So let's figure it out. So if this goes around, what's the velocity? Velocity is how much distance over how much time. So over 27.3 days, over one period, it would have went through one circle. So that would be 2 pi r. Which r should I put? Well, the r, not the radius of the Earth anymore, but yeah, so that was a mistake, right? It's the distance from the moon to the Earth, right? So from the moon to the Earth. Right? So here, again, it is the same r from the moon to the Earth. Okay, so you can use trigonometry to figure this out. So distance is something you can usually figure out with trigonometry, or actually you could, but this is another way of going about it. But so let's plug this in over here, right? So if we plug this in over here, we get 2 pi r. I'll just keep it simple. That's the same r. T squared equals to g m over r. And now let's rearrange ourselves and, for example, put t squared over here. And there is r cubed over here. Gm stays here. And there's a 4 pi square over here. Okay, you can double check my algebra. If I put a brackets around here, right? So this is the distance from the moon to the Earth, remember? So if I know this, right, you can convert that to seconds. And this is something, right, we know, I just said we can measure the mass of, we can figure out the mass of the Earth by looking at the density of rock and estimating the volume. Now we can calculate what's the distance between here, okay? And this is a general formula. Let me rewrite it in a more general form. 4 pi squared t squared, like this, okay? Yeah, and you can, for example, the capital G over here, you might ask, how will I know that? Well, the capital G can be figured out from, for example, there, right? So if you know this, you can measure this, you can measure this, and you can, right, so this is roughly 9.81. This is you get from the curvature, right, roughly 6,400 kilometers. This, like I said, you can measure from the density of rocks, which is around 10 to the 24 kilograms. And now you can get what that universal constant is. So you will know this. And you can now go into the sky and measure the mass of planets you have never been to. How do I know? For example, if I want to know now the mass of the sun, right, then I can look at the sun as an orbital motion, right? So remember, where does this come from? It's really just this, right? And this is putting these two together, these two concepts we've just learned together, right? And that will immediately give you this after one step. And from this to this is me just plugging in the speed is distance over time, okay? And you plug in speed equals distance over time, and within one more step, you get this. I just cleaned it up a little bit. So what do I put over here? This is the mass of the source, right? So I can have mass of the sun and 4 pi squared, G, okay, equals to R. So the R is the distance from the Earth to the sun, and T square, right? So, and T is the period that the Earth needs to go around the sun, right? So how long is that? Well, that's 365 days, 0.25 or whatever. You can depend on how accurate you want it to be. That's easy to measure as well. And you can change that into seconds. So if you know this, and from trigonometry, you can figure out what the distance is. And now you can figure out how the mass of, what is the mass of the sun. Imagine how powerful this is, right? And this, what I put over here, is called Kepler's law. Okay. So Kepler was the first guy who, again, put this together and utilized what Newton just discovered. Same period, a scientist as Newton, put the ideas of circular motion and what Newton discovered about universal gravity, and he was able to figure out the mass of other stars, other planets. You can figure out how far things are. Essentially, the law is often written as r cubed is proportional to t squared, right? So what that means is, this is a constant. So for example, now you want to figure out how far away is Jupiter, right? You can easily do that. So Jupiter goes around the sun, right? Like this, or Saturn or whatever, right? Let's say Saturn. So I can distinguish it with some rings. So if I want to figure out how far away is Saturn, well, I just need to measure the period, because if something is proportional to something, well, I know exactly what that constant is, right? This is, but even if you don't have, there's an even simpler way of figuring that out. Is, for example, I can put the radius of Earth, right? What is proportional? Proportional means some constant times this, right? So let me write this twice. And I can put the radius of Earth from Earth to the sun. And if I put the radius there, if I put Earth there, I need to put Earth here. If I put Saturn here, I need to put Saturn here. Okay. Now, if you divide them, you will get our Earth over our Saturn cube. The k's will cancel out, and you'll have T Earth over T Saturn squared. Okay, what do you know? What can you measure, in other words? You can measure, well, we already know the Earth's distance to the sun. We just talked about that. The period around the Earth, of the Earth around the sun is 365 days, essentially, right? And this is something you can measure. You can, from Earth, you can sort of look how long does Saturn go around the sun once. You measure that, and now that will figure out the radius of Saturn, right? And you can take that once you know this relationship. So this is Kepler's law. I think Kepler then just sit there, right, for the next month, because again, nothing better to do back in the days. There's no internet and Twitter. So you will start to go out and look at all the different planets, and you can figure out exactly with this, just by measuring how long it takes for them to go back to the same place, which is something you can do with a telescope at home. And you can figure out the distance of everything else. So look, with what we just learned about a simple law of gravity, it's so much more than that. You can now extend our human knowledge way beyond Earth and understand how the solar system works. All right. So we'll wrap up by talking a little bit about the concept of weightlessness and how everyone is using that word wrong.